Okay, YouTube, in this video we're going to reconfront how to solve a quadratic inequality in one variable. That is to say, some quadratic expression here, either greater than, less than, greater than or equal to, less than or equal to some constant value, which traditionally we set this equal to 0. I don't say equal, but have a 0 on the right side. So one really convenient way of doing this is to solve it by graphing. And the way we get this to work is essentially to consider this first. If we said solve 2x squared minus 4x minus 1 is greater than or equal to 0, what I want you to understand is that traditionally we do indeed have a y value over here. And so we would say that really if what we're saying here is this is our y value, y is equal to all of this stuff. Really what I'm looking for are all the x values that cause our y value to be the thing that is greater than or equal to 0. So what we're going to do is this. We're going to graph first the equation y equals 2x squared minus 4x minus 1. And then we're going to see that the original inequality that we're trying to solve is after the x values for which the y values of the parabola happen to be greater than or equal to 0. So let's go ahead and start with this. When we want to solve this, we'll graph it as if we had the equation y equals 2x squared minus 4x minus 1. So the first things we want to do here are ascertain where the axis of symmetry and vertex are. Since this is in standard form, we could say we know our a, our b, and our c values here. We'll go ahead and start by finding the axis of symmetry, which is at negative b over 2a whenever it's in standard form. So we get negative b over 2 times a, where our b value is a negative 4, and our a value is a positive 2. So in this instance, we end up with this. We get a positive 4 over positive 4, which is 1. So immediately, I'm going to go over to my graphing coordinate plane here, and I'm going to put in a dotted line, a dashed line for our axis of symmetry at x equals 1, and be sure to label this. The other thing we need to find is the vertex. Now the nice thing is that the vertex has to lie on the axis of symmetry, and so its x value must also be 1. We're just going to need to now go find what our f of 1 would be if we had this as an equation. So if we say f of 1 here, wherever we see an x, we're going to substitute in a value of 1. So we have 2x squared, where it's now 2 squared, minus 4 times 1 minus 1, which gives us 2 times 1 squared, which 1 squared is 1. So 2 times 1 is 2. So we have 2 minus 4 minus 1, which gives us here negative 2 minus 1, which is negative 3. And so I notice here that negative 3 would be where this vertex of this parabola would lie. So I'm going to finish graphing this up using our a value here. I know that a is 2, which means we have a vertical stretch by a factor of 2. So whereas as we go right 1, we usually go up 1 with our parent function, we're going to go right 1 and actually up 2 to get to this point right here. And because of symmetry, I would say that we have a point right here as well. So now, why graph this in the first place? I can do a better job than that. There we go. There we go. Why graph this in the first place? Recall that what we were trying to do was solve for all of the x values that make this statement true. And so if what this expression on the left is representing the y value or the overall y function, then what we're really saying is find all the x values that cause our y values to be greater than or equal to 0. So what I want you to understand is that our y values are positive y values up on top of the x-axis, and they are negative y values down below the x-axis. This is kind of common sense, and we'd say it'd be at a height of 0 exactly at the x-axis. So what we're really trying to do is find all the x values that when we plug them in, our graph happen to be above the x-axis here, or greater than or equal to 0. So for step 2 here, it says find the zeros or the critical values of the function and label these on the graph. What we're really looking for here are these zeros right here, because what I can tell you is these are the x values at which our graph goes from being on top of the x-axis to being on bottom, or vice versa from being on bottom to being on top. In other words, where it goes from being positive to negative or negative to positive, it has to happen at a 0. And so if we're going to find all the x values that cause our graph to be above, say, the x-axis, by the way, they're all the x values that are here and here. The reason why is because look at our graph. It's above the x-axis here. It's greater than or equal to 0 at these points right here on our graph. So the x values that cause this to happen are to the left of this x value right here, which we don't know what it is yet, something comma 0, and this x value right here. So this is why it's important that we actually solve for these zeros. So to solve for the critical values, or the zeros, again, we're going to start by setting our initial expression equal to 0 and solving this. So now, whereas in our last example, I say factoring worked very well. In this example, I noticed that this doesn't factor. And I also can't use square roots. So I'm inclined to use the quadratic formula then, which always works. So our a, b, and c values are respectively 2, negative 4, and a negative 1. So putting this together with our quadratic formula, I'm going to go ahead and try to utilize as much space as I possibly can here. So we'll start over here. We get x equals negative b plus or minus the square root of all of this, b squared minus 4 times a times c all over 2a. It's negative b over 2a, the very same negative b over 2a we're looking at here. We say plugging in our b values, we get negative 4, negative 4. A is 2 and 2, and our c value here is a negative 1. So what we end up with here is this. Well, then our solutions, or our critical values, must be negative, negative 4. So this would be 4 plus or minus the root of something all over 2 times 2, which is 4. So let's work on what we have inside this radicand. We say negative 4 times itself is a positive 16. I notice that with this product here, I have two negatives, the negative 4 and the negative 1, which means the whole product comes out to be positive. And 4 times 2 times 1 gives us an 8. So further simplifying this, we get 4 plus or minus the square root of 24 all over 4. And in terms of perfect squares that go into 24, I can think of 4 does. We say 4 times 6 all over 4. So now we'll extract the square root of 4, which is this 2 right here. And rewriting this, we get 4 plus or minus 2 root 6 all over 4. And because these are all divisible by 2, we'll reduce them. We'd say 2 goes into 4 twice, 2 goes into 2 once, and 2 goes into 4 twice. So our final solutions are 2 plus or minus the square root of 1 times, 2 plus or minus 1 times the square root of 6 all over 2. So these are the critical values that we see right here. So for the sake of simplicity, what we're going to do is essentially this. We're going to say, well, then what would this equal here? So I'm going to write in parentheses everything on top here. So we'd have 2 plus the square root of, you notice this gives us a new beginning parenthesis here. So we're going to need 2 end parentheses to encapsulate the top. And this is all divided by 2. Enter, and then I'm going to hit second enter to re-pull up the thing we just typed in, and I'm going to scroll back over, and I'm just going to change this to subtraction. So it looks like we get 2 decimal values here. The one on the left is negative about 0.22. So we get about negative 0.22 approximately. And then on the right side, this other 0 over here, I'll get this out of the way, it looks like about 2 and some change. Well, it comes out to be 2.22-ish. So about 2.22. So if we wanted to find then, what are all the x values that satisfy this initial inequality? Remember, we're finding all the x values that make our expression here greater than or equal to 0. In other words, our y values greater than or equal to 0. And just by observing on the graph, we say, well, those are above the x-axis here. They're greater than or equal to 0 there. So we're going to say it's all x values from here over. And from here over, when we plug those in, we got y values greater than 0. So our initial graph here tells us that our solutions must be either these. We say x is less than or equal to, it could be or equal to, given this initial or equal to relationship here, this negative 0.22. And we could say and also x values that are greater than or equal to, or to the right of this x value here, which we determined as 2.22. Those, when plugged in, caused our y values to be greater than or equal to 0. Cheers.